All right, welcome everybody. Today we're going to be working on hypothesis testing, both for one populations, and we'll get a little bit into introducing two populations as well, since the process is so similar and using our same tools, we can get these results. But in hypothesis testing, similar to our work with confidence intervals, where we're using sample data to try to estimate values or possible range of values that the population parameter would be between. Now with hypothesis testing, we're using sample data to kind of test whether those population values, those population parameters are accurate, or maybe they've shifted in some way, testing these claims that we have about a population, these kind of assumed values, these values that we kind of are using as true for the moment, and hoping or possibly checking to see with sample data if those values have changed. So we'll go into some notes as well as some practice problems involving hypothesis testing. All right, so going into our hypothesis testing, as I mentioned, right, what we're going to kind of do is we're going to use sample data to test, right, hence the testing, right, if population parameters, right, those values that we compute using the entire population's worth of data, right? So that's going to be the mean, proportion. Later we can get into the standard deviation sigma, or even variance sigma squared, so on, right? Testing to see if these population parameters, right, are, I'm going to say, valid, right, are still true, or possibly there is some shift. There's going to be some claims by researchers that maybe the value for our parameter has changed, and we're using sample data to test, okay? And so when we're going through hypothesis testing, we have typically this kind of these five main points to go through for this process for hypothesis testing, right? And so the first step is that we want to identify our hypotheses, right? So these are the statements, those ideas that we're going to be checking, that we assume to be true first off, and then we're going to be checking as we go on, right? And so for hypotheses, the first hypothesis is H sub 0, right? This is our null hypothesis. Okay. And with our null hypothesis, I'm going to put here in green, there's notes here. With our null hypothesis, this is always going to have that equal sign, right? And so with our null hypothesis, this is where here, this is going to be our assumed, our kind of agreed upon, or the assumption that we're working on, value for the parameter, right? So this is that kind of general value that so far everyone agrees to. Maybe it was done with a previous practice, a previous research project that they've gone through and identified this value for a parameter. So with our null hypothesis, that H sub 0, that's going to be where we have mu equals this given value, right, for the mean. Or if we have a population proportion, P is equal to that, right? This percent of citizens hold this kind of belief, right? This proportion of businesses satisfy this characteristic, so on. And we're going to present that as a decimal after the percent, right? Or likewise, even if we're talking about standard deviation, variance, so on, sigma. And this is going to be, again, our assumed value, right? This is going to be the value for the population. And common is what we're going to check to see if this value has possibly changed, has shifted at all, right? So there's our null hypothesis, one of those three statements, depending which parameter we're dealing with. Then whether it be h sub 1 or sometimes in different texts, we see h sub a, this is our alternative hypothesis. And for our alternative, right, as it kind of says there, this is that alternate idea, that possibility of change. So now in this case, this is where we're going to use an inequality symbol. This is where we start to see where possibly maybe we think that value has gotten small, that is less than that quantity, that is greater than, it's gone up, it's increased, or just that it's different, that maybe it's changed, we're not sure if it's gotten bigger or smaller, but definitely we don't think it's the assumed value that we have started with, right? And so with these, again, we're going to address that assumed value. For our alternative hypothesis, I'll use h sub 1 for my notation here. For that alternative hypothesis, we're going to see, right, that mu is less than, and now in this value here, you're going to go back to, this is our value from our null hypothesis. Right, because we're always comparing to what we assume for the population. The sample data that we're going to see, the sample values that we have are going to come up later in our process. For now, we're kind of assuming this is what's being held true for the population. And our ideas, our possibilities, our alternate results that possibly could occur, right? And I'll go with the other value, right, for proportion. Maybe it's greater than, same deal, same action. Take that value from the hypothesis. Maybe we think the percentage is greater, has gone up from 50%, 55%, and so on. Okay. Whereas decrease has gone down. Or somebody's not equal to. And again, I'm using my different symbols. We're not always going to have greater than with the proportion. Mainly here, I'm focusing on the inequality symbols we're using. The parameter will identify with our problem statement of which symbol we need to make sure we use. And it's always going to be the population information with our hypotheses. All right, so this is the first step. That first action in our hypothesis testing is identifying our hypotheses, okay? Using those symbols primarily. All right, so the next step here, now this is where our sample data comes in. Step 2, now we're going to look at our test statistic. And with that test statistic, okay, this is going to be our value computed, right, based on our sample data. And really here, this is where we're going to see either a z-score, that t-distribution, t-score, right? Or when it comes into standard deviation, we're going to get this chi-square score. Okay? And so often when we're looking at these different values, we're going to see a z-score when we're doing proportions. Or likewise, if we're doing the mean and we actually know the population standard deviation, which is pretty odd, is not very common to know the population standard deviation, not know the population mean. So that's why we don't really necessarily use that too often. The t-score, that t-distribution, very similar to our confidence interval work. We're going to see the t-scores being used primarily when we have the mean. And that chi-square score, another distribution, we had the normal, that z distribution. We had our t-distribution, that student t-distribution. And now when it comes to standard deviation or variance, another distribution shows up, this chi-square. This is the Greek letter chi, C-H-I, how you spell it out in English, but the chi-square score is when we're doing standard deviation or variance. Okay, make sure I got my spelling right. There we go. Okay, sigma sigma squared, just for that notation, right? And I guess I suppose for the mean, we're doing mu. For the null hypothesis, right, proportion, p. So, okay, and so then we're going to base these values, these test statistics, kind of looking at those distributions. And as we had, right, when it comes to proportion, if we're doing a test for proportions, our test statistic is a z-score. And when we calculate that z-score, we're going to take our sample proportion, right? So we did a sample of 50 people. Of those 50, right, this percentage, right, this many successes, x over n, so on. That sample proportion, p hat, minus this value I'm going to call p sub 0. This is our population proportion from the null hypothesis. That same value from step 1, that null hypothesis value we're going to use here, and then we're going to divide by this square root, and that square root we're going to have here that same population proportion p sub 0 from the null hypothesis times its complement 1 minus p sub 0. Right? Sometimes in subtext you might see that called q, right? The complement of your population portion. And then we're going to divide that by n, your sample size. And so in calculation, we'll do that subtraction first in the numerator. We can do the square root work from the denominator separately, and then bring those together, type it all in at once, is being careful with the order of operations, so on. Okay. But here's our formula we can calculate, but once we'll go forward, we'll see StatCrunch. A lot of these programs will calculate it directly for us, and we don't necessarily need the formulas. I bring in the formulas just so we can identify how those results show up. Okay. So there's our test statistic, right? There's value for our sample data that we're going to use to compare to our population value. Then for the mean, we could do, if we know the population standard deviation, truthfully, right, going back to our work in earlier chapters, we can calculate the z-score, where our x is our sample mean, right? Then we have our population mean that we're trying to identify, that's from the null hypothesis, divide by sigma, the population deviation, over the square root of n, we get that z-score. But most often when it comes to the mean, we're not going to have the population standard deviation. We'll only have sample standard deviation, so we're going to see a t-score, that t-distribution being used. And so we talked about, right, x bar, our sample mean, minus mu, again, that population mean, that's from, I'll use my symbols this time, h sub 0, the null hypothesis, right? Same deal there. And then we're going to divide by s, our sample standard deviation, divided by the square root of n, the square root of your sample size. Okay. And then lastly, we can also deal with a chi-square if we're going to do a hypothesis test for standard deviation, for variance, so on. That chi-square score, get that chi-square is going to be equal to n minus 1, that sample size, minus 1, times your sample standard deviation squared, or your sample variance, and we're dividing by your population standard deviation squared, or your population variance in denominator. Okay, so remember that notation that we have here. S is your sample standard deviation. So there's our sample data coming in. Or depending, and make sure, be careful with your reading of the problem. If it's a sample variance that they provided, that means they've already done the squaring, right? And then similar, sigma population standard deviation, that value that we're assuming to be true in our null hypothesis. Or again, if they've already done the squaring, they might provide you the population variance. So in this case, this is the value based on our sample data. Primarily, we're going to talk about proportion and mean. Later, we'll get into standard deviation, right? But it's a value that utilizes our sample information, okay, to help identify, okay? Let's focus. All right, so then once we get that test statistic, now we're going to start talking about this kind of comparison, right? And so we have two options. We have option one, using critical values. Okay. Or option two, p-value. And with more software that we use, the easier it is to use these kind of special programs on our computer, even in calculators now. We start to see p-values getting used a little bit more often. And certainly with two populations later, we'll do that. But critical values, a nice visual, kind of bringing us back to our visualization with that normal distribution, the t-distribution, so on, in this comparison, okay? And so when we start to think about this p-value or critical value, in order to make our decisions and so on in the next step, we're going to need to have a value for alpha, which is our significance level. Most commonly, our values for alpha are going to be like 1% or as a decimal 0.01 or 5%, 0.05, but similar to our work with confidence intervals, right? How we can use any confidence level we wanted, 95%, 99%, 92%, so on. Significance levels can be any percent. Most likely though, 1%, 5% show up. We can have 10%, okay? And you'll see that similarity, right? Because we have that alpha with our confidence levels, 1 minus the confidence level. So just like having a 99% confidence, that 0.05, that 5% significance, like a 95% confidence interval, so on, kind of seeing that similarity. And a key statement here is this alpha, right? This is our type 1 error probability, right? So that's the probability, chance that we make an error, we make the wrong decision, the wrong conclusion based on our work, right? Because based on our sample value, we might have one rare sample where our value is much higher than what's normal in the population. So we're gonna get this error because we're making the wrong decision because we had some unusual, some rare event in our sample. Okay, so there is a possibility that we're making the wrong decision, but we're hoping, right, that we're not going to make that error, that our significance of making such error is small, so on. Okay, I'm making this comparison. All right, so with that said, with our critical values, okay, doing this first time, our critical value method, depending on whether we have that normal distribution, the z, or the student t distribution, or later we can talk about the critical values using the chi-square distribution. But with our critical value, we have our distribution curve, right? So that's that z, that t distribution, so on. And when we look at those critical values, we're kind of identifying that, okay, if I have that amount of area alpha in that tail, that cutoff value for it is your critical value, okay? And so looking at this distribution, we have these possibilities do my best to redraw that normal distribution or that t-distribution, right? Where maybe we have the area in the left tail, the area alpha in the right tail, and again, that cutoff value, that critical values marks there. Or similar to our confidence interval work, we might separate that amount of area evenly between our two tails. Let's see, CV for the left, critical value for the left, critical value on the right, okay? And so these two are our one-tail tests, and we kind of identify that if we have in our alternate hypothesis that we have that our parameter, I'm going to use mu for my example, is less than this value. This means that we're going to have a left tail test. All right, we're putting all that significance, all that area on the left side. You can probably guess what's going to happen here. If our inequality symbol in the alternative hypothesis, a sub a sub 1, is a greater, that's going to be a right tail test. That inequality symbol pointing us in the direction that we're going to put that area on that right side. Or if we're going to split it, this is where we have the two-tail test. We have that area split between the two. That not equal to, I kind of think of it, okay, we're separating, we're cutting that in half to put that amount of area evenly between the two, okay? And here's our two-tail test. All right, so with that two-tail test, one-tail test with left side, right side, we're going to critical value, okay? And so based on having that much area, kind of like we found those cutoff values back with our normal distribution work before, having that amount of area in the tail, we can go to our particular distribution, whether it be the normal z distribution, that student t distribution, using those calculators, so on, to find the cutoff value, that z-score, that t-score, to identify that amount of area in the tail, okay? And so then, once we have those critical values identified, what we start to see, and again, kind of using that left tail test as my first example, once we go through and we have that alpha, that amount of area in our tail, we see our critical value. Now, when it comes to making that decision, as we go through, if I see that my test statistic, that value computed based on our sample, is in that shaded region, right? Or I'll use that left tail test as an example. It can be the same when it comes to our right tail test or even the two tail test. If our test statistic is outside, that shaded region beyond the critical value, right? It's outside that critical region, sometimes it's called, okay? When it comes to making our next statement, step 4, our decision, okay? Our decision's either to reject the null hypothesis or we do not, or you fail to reject the null hypothesis. And we're always comparing to the null hypothesis, right? What we're assuming to be true for the population, because we were using sample data to test, to check if the population value is still valid or if it's shifted, so on, okay? And so looking at these statements, looking at these results, that when our test statistic is in that critical zone, critical region, when it's in the shaded space, right? That's going to be where we reject the null hypothesis, whether it be on the left tail or it could be in a right tail test, right? My test statistics here, we're going to reject either side with a two tail test, okay? But when your test statistic is outside the shaded region, that's when we do not, or you fail to reject the null hypothesis, right? And so what this kind of idea is, and we'll get into with our summary, is that when we're rejecting the null hypothesis, we're rejecting that assumed, that population value that we've been working from that everybody assumes to be true at the moment. So we're rejecting that. Our sample data is different enough, it's significantly different that we say, okay, that population value must be invalid. It's not true anymore, right? And we can go further studies to verify, but that's kind of our initial check to see if that population value can be rejected, right? If our sample value is outside, it's not different enough, right? It's not in that space where it might be unusual to get a result. We're kind of in that body where we anticipated the majority of value would be found. We do not reject, right? We're going to keep that population value. We're not rejecting it. We're going along. That must still be true, must still be valid for our population. Okay, so that's the decision part. So I'm kind of working with step 3, finding those critical values, using those distributions, that inverse process, given an area, finding the cutoff value, the critical value, and then using that to compare with our test statistic, our sample data. So that was a critical value method. So then, similar, when we want to do the p-value method, okay, that was critical value. So now for our p-value method, with our p-value method, the key statement here is that we're going to compare your significance level that alpha to our area from the test statistic. Okay. So when we start to see in that calculation, whether we have that left tail test, that right tail test, so on, right? We can have our test statistic that t value, that z-score from our step number 2, right? Those values that we computed here, depending on which distribution we're using, right? Then we'll calculate that area for a left tail test, left side, right tail test, right? Two tail test, you get your test statistic area, you double it, right, to get those two tails, that balance. And so this area, that's going to be the p-value. So that's what's being computed with a p-value, whether it be the normal distribution, t-distribution, that student t-distribution, or again, we can go further with the chi-square distribution or standard deviation. But once you get that p-value, you're going to make a comparison, okay? And so then when it comes to making that decision, when we see that our p-value is less than alpha, right? So the probability of getting a sample value, a test statistic, a sample data in the space, that probability again here is smaller than our significance level. That p-value is less than alpha. That's when we reject the null hypothesis. Okay? That's our decision. We're less likely to get a value here than make an error. Okay? Then the opposite, if our p-value is bigger than alpha, right? So we're more likely to get that value than make an error, right? We're more likely to make an error than get a value there, okay? That's when we do not reject. The null hypothesis. Okay. And so it kind of falls into place. It's very similar. I'll let you kind of look that through with a critical value. Okay. When that critical value is below, or our test is below the critical value, we're going to reject, right? That area is smaller. That test statistic is beyond your critical value. Okay. This case, our test statistic is outside of that critical zone. We're not going to reject. Okay. And from there, once you make that decision, okay, and again, you can use either one of those two methods, the critical value method, kind of looking to see where your test statistic was in relationship to your critical value, looking at that critical zone to make your decision, or the p-value, which we'll kind of see a lot more often with our software systems. Okay, once you make that decision, though, then we're going to do our summary, right? So this is the part that kind of takes a little more time. This is now our wording, our summary, okay? Or sometimes I'll call it the conclusion. Right? I know we've made a decision, so that's like a conclusion. But now in this case, with our summary, our conclusion, I want to go back to using the wording, that kind of particular application statement of the original problem. Okay. And there's going to be a lot of examples that we can read in the text. You can probably find online some examples as well. But in this case, we kind of start to use these kind of phrases that there is sufficient, or my other example, I'll say like there's enough evidence. And if we're rejecting that null hypothesis, right? To reject, and we go along with that null hypothesis, putting it into words, right? That population mean, or proportion, standard deviation, okay, is, I'll put dot, dot, dot. Now that's where the wording from the problem comes in, okay? Or likewise, if we're not going to reject, there is not sufficient, or I say not enough evidence based on our sample to reject. And I'll put my dot, dot, dot here. Continue with that wording from the problem. And again, this part, the summary, takes some time to kind of get used to that wording, how we phrase that, how we kind of understand. But there's always, again, based on like our decision, that null hypothesis, that assumed value for our population. All right. So with that said, let's go through an example or two, looking at some of this information. We can write up some more examples as well for you to look through. And as we go through, I'll switch over to StatCrunch as well for these calculations, right? And so I'll have these handouts available to view as well. There's our 5 steps, those procedures, okay? The different test statistics that we can use to calculate. Again, we can also do one for the mean, mu, with the z distribution if we happen to know the population distribution, sigma. But as you can see, most commonly we have our sample data. Let me try to zoom in here. I know it's a little bit small for review. All right. So let's go through this example though. So it says in this first problem that a survey in a recent newspaper article stated that 38% of Americans said that they will not eat carbs this Thanksgiving. Okay, so this is an example I had done around Thanksgiving time, right? And again, with all the dieting trends and whatnot, maybe people are not going to eat carbs, right? And so the dietitian thinks that this percent is far too high. Like more people are saying they're not going to eat carbs, but that's too high. This dietitian thinks that the percent that don't eat carbs is going to be much less, or not much less, but at least different, less than, I'll say, pardon me, than that 38%, right? And so with that percent, I'm already starting to think about proportions, okay? And so in this case, a random sample of 150, so there's our N, a random sample of 150 residents was selected. 48 said that they're not going to eat carbs, so 48 people out of the 150 have that characteristic that they're not going to eat carbs. Using 5% significance as our alpha, let's test the dietitian's claim that the proportion of Americans that will not eat carbs is lower, will be lower than that 38%. Okay. So as we go through that 38%, okay, that value, this is going to be our P sub 0. That's the percent that we're assuming to be true for the proportion. The dietitian, this researcher, this person has an idea that that proportion should be lower. That's what we're trying to compare to. So that's what we're assuming to be true. Okay. Looking through some of these other values, right? A sample of 150 people, because there's our N. Of those, 48 are not going to eat carbs. So there's our X, the number of successes, the number of people that have that characteristic. Our P hat, our sample proportion, X over N. We'll compute that 48 over 150. We're going to test, okay, at the 5% significance level. So our value for alpha, 5%, or 0.05. Okay. So I know it's a lot of information to kind of go through, but let's start to look at this example then. As we start to look at these pieces, right? Looking at our 5 steps. The first step that we're going to go through, step 1, okay, I'm going to go Roman numerals, are hypotheses. So for those hypotheses, starting off, the null hypothesis, H sub 0, always equality. Our proportion we're talking about, so our parameter P, we're going to assume that it's going to be that 38%. I'm going to convert it to a decimal right away. So that's what we're assuming to be true. Going by that article, that's what the population is agreed upon at the moment. But now the dietitian has a different idea, an alternate hypothesis, right? So for our alternative hypothesis, H sub 1, same parameter P, that proportion. But now they think that it's going to be lower than that 38%, lower, less than, right? So this alternative hypothesis is that that percent, that proportion should be smaller than 30% or at a decimal 0.38. The proportions, the common habit in rounding is to keep 3 decimal places, okay? Which is going to show when we start to deal with our test statistic next. And so with our test statistic, step 2, as soon as we're doing proportions, okay, our test statistic is going to be a z-score, and it's going to be that p hat minus p sub 0 all over this big square root p sub 0, that null hypothesis proportion times this complement, 1 minus p sub 0 all over, and that sample size. Let me slide that up a little bit. Okay, and so with that set up, okay, as I mentioned up here, we can calculate that test or that sample proportion, x over n, 48 over 150. And Off to the side here, I'm using my scientific calculator, 48 over 150. And we're getting, thankfully, a nice simple terminating decimal, 0.32. Had we gotten some long decimal, we can keep that, or again, the common habit, we round to 3 decimal places. Okay. We have our value from 150. And so as I start to calculate, I'm going to take my sample portion, 0.32 minus the null hypothesis proportion, 0.38. Now we're going to divide that all by the square root, big fraction inside. Null hypothesis population proportion, 0.38, times this complement, 1 minus that same 0.38. If you want to do that calculation ahead, you can, right? 1 minus 0.38, 100% minus 38%, you're going to get 62%, 0.62. You divide by the sample size, which was 150. And as a helpful thing here, you always subtract first, then worry about that division. In Desmos, we can kind of share that screen and we can see, okay, that calculation. Let me share that real quick. See if we can't do that. All right, so now we should see my Desmos calculations doing, oh, not square root yet, there's my t hat, my sample portion, as you can see, but now I calculate z, we're going to need a fraction division in the numerator, 0.32 minus 0.38, p hat minus p sub 0. Now we have our big square root in the denominator, fraction inside of there, division is going on there, 0.38 times 1 minus 0.38 all over 150. And there's our long test statistic, the z-score. And as we're kind of used to doing, let me copy that down real quick. When it comes to those z-scores, I'm going to stop sharing now. Having a long decimal, right? So there's my unrounded value. And then for our test statistic, that z-score, when it comes to normal distribution, our z-scores here, we're going to round to 2 decimal places. Right, so rounding to 2 decimal places, 1, 2. That 3 says that 1 can see this the same, negative 1.51. Right, so there's our test statistic. And so even going back before, right, kind of that idea with z-scores was kind of considered unusual. Z-scores that are bigger than 2, right, less than negative 2, that's when we start to get to some unusual quantities. A z-score of negative 1.51, right, that's not too bad. It's like only 1.5, 1.5, right, 1.5 standard deviations below the mean, which isn't unusual. But that's kind of tying into what that z-score represents for us, that standard deviation idea, so on. But there's our test statistic. Hypotheses using the parameter symbols for proportion, had it been for a mean, mu, right, so on. And then our test statistic when it comes to proportion is going to be a z-score. All right, so now with that said, next up, we're going to do our p-value or critical value. So now, in this case, now I'm going to start to use StatCrunch, okay? Because if we're looking for the critical value, that z-score cutoff, we're going to need StatCrunch for that normal distribution calculator, or likewise, thankfully, StatCrunch has tools similar to our confidence intervals, right? Tools built in for hypothesis testing right away, okay? So I'm going to start to share screen again with our StatCrunch calculator this time. And here we are, okay? So now looking at StatCrunch, similar to what we had seen with our confidence intervals. Now, we're going to look at either z-stats. That's going to be when we're dealing with the mean and we know the population standard deviation, very rare. More commonly, t-stats, one sample, we have the mean, right? With summary, we'll see that in another example. Or in this case, since we're dealing with proportions, very similar to what we do with confidence intervals, right? Those statements, we're going to do proportion stats. We only have one sample, one population we're dealing with, okay? And we're going to go with summary. Very similar to what we saw with confidence intervals. If we're doing a test for standard deviation or variance, right? Standard deviation is kind of hidden, is using variance, and we'll see that work there. All right, so with our example though, similar to what we saw with confidence intervals, we're doing proportions. So we have proportion stats. We have one sample, one population that we're dealing with. We're going to go with summary. And so what we had talked about before when we had confidence intervals, right? We highlighted that dot. Now we're going to stick to hypothesis tests right there in front of us from before. And so now we start to input, right? So our number of successes, our X values, right? Your number of observations, your sample size, that's your N. And then we'll put in from our null hypothesis that quantity. Okay, so let me start to fill in though. For our example, our number of successes was 48. Our number of observations, our sample size was 150. We are doing a hypothesis test, our null hypothesis, that 38%, 0.38, right as a decimal. And then our alternative hypothesis, I know I did H sub 1. The calculator here uses H sub A, right? We have that less than. We think that dietitian, I should say, thinks that claims that that percentage is too high, so it should be less than 0.38. I'll have it show the critical value. That way it's doing that work to get the critical value if you want to do it. Our significance level, 5%, 0.05, so that's good. You can change that as necessary. Show the critical value. I'm not worried about the graphing. We'll compute. And there we go. So, right, so now in this case, here's our results. There's our proportion of successes, right? So there's our P. Null hypothesis, alternative hypothesis, right? So just copying that down for step 1. We're looking for proportion. There's the count. That's our number of successes, X. Total, your sample size, N. Sample proportion, there's our P hat. Standard error, that's the standard deviation if we're going to use it, but we don't need that, right? Our Z-stat, that is our test statistic, right? Only a few digits shown here, but again, with rounding, we see the same results. That critical Z-scores, there's our critical value. There's our cutoff value, negative, right? It's a left tail test. We expect negatives there. And now our p-value, right? So whether we're doing the critical value method, there's our critical value. Don't forget my negative, there's our highlighting, right? P-value method, like so, right? So taking those values, we have all that data there, all information. Then now we can use that to finish up our work with the hypothesis test, okay? All right, so I'm going to go back to the notes. There's our information, all right? And we'll borrow that result there, okay? So using StatCrunch, remember that's going to be under the stat menu. And then we're going to either look for, depending on what we're working on. In this case, this was proportion stats. Right? Proportion stats. We're dealing with one population or one sample that we've identified. And we're going to go with summary. Later, or in other problems, you can work on, or maybe if you're given raw data, in particular when it comes to like the mean or standard deviation, right? Having a list of data instead of having to calculate your sample mean, sample standard deviation, which you can, similar to what we did in chapter 3, okay? What we can do instead, put that data into a column and then have it refer back to that column. But we're going to go with sample with summary, and we'll input that information, okay? And so based on that work, going through those calculations, inputting that data there, right? And again, for the mean, it'll look very similar. We can see a quick kind of run through with that work later. But looking at that result, right? That Z-stat, just kind of highlighting here, this is our test statistic. Then it has your critical Z. This is your critical value. And then, of course, directly p-value. Nothing really extra to say there, but I'll put the highlighter there, right? That p-value. Okay. And so from our values, what we saw that z-stat negative 1.51, 3942, right? There's my unrounded value. That same result we saw back in step 2. You can call it z sub p hat if you wish, right? That was that step 2. The critical value, negative 1.64, 48536. And you might remember that from our confidence intervals, right? If we have that 5%, that 90% confidence level, that z score, that z sub alpha 2, 1.645 or 1.65. Textbooks rounded differently, use that value differently. And then our p-value, that's 0.065. Okay, so there's our value for p. I'll put in blue, 0.065, so on. Okay, so there's those values. These are the quantities from StatCrunch. Unrounded, rounded values, so on. Okay, and so when it comes to making our decision, step 4 there, right? Looking at our p-value, looking at this value for alpha, that significance level, 0.05, we can put a 0 when we can. Comparing those, right? Working left to right, same digit in the ones place, same digit in the tenths place, okay? Get that to focus. All right. Comparing those then, now getting into the hundredths place, 6 is bigger than 5, so our p-value is greater than alpha. There's that comparison. So for our decision, when your p-value is bigger than alpha, you're going to say we do not or we fail to reject that null hypothesis. Okay, so there's our decision based on that information, those values computed using StatCrunch. We're not rejecting the null hypothesis. Okay, had the p-value been less than alpha, how we got like 0.015 instead, then we would say we reject, right? But now because p-value is bigger, we do not reject. So now this is the part that students always have some questions, some trouble, some time to develop, which is our summary, right? Our summary for our conclusion. So based on our sample data, right? We can't reject that null hypothesis. So even though this dietitian thought that that percentage should be lower, right? We're not rejecting that value. So in this case, for our summary, is that, right, there is not enough, or I'll go back to that word sufficient, either way is fine, evidence, right, based on our sample to reject that those proportion of Americans that will not eat carbs, carbohydrates, this Thanksgiving, right, or during Thanksgiving, is, right, because we're still going along with what that population and proportion was assumed to be, right, is at 38%, right? We cannot support that claim that that proportion, right, that percentage from this, right, that claim of the dietitian, that that proportion, that percentage should be lower. Right? That's kind of what we're identifying. The more formal conclusion summary, though, is always based on that null hypothesis. We don't have enough evidence. We don't have enough data to reject, to go against that assumed value for your population. Okay. And a lot of that work, right, coming from StatCrunch, similar to what we did with our confidence interval, but there's that longer process, right? Starting with reading through the problem, gathering up those values, hypotheses first, test statistic. StatCrunch finds that same test statistic. So even if you want to kind of jump into StatCrunch right away, we can do so. Watch those values that you're inputting. Then once we have those results, though, right, that decision, that comparison of your p-value to alpha, we can draw that distribution diagram and see that that test statistic is outside that critical region based on our critical value. So we have that same conclusion that we don't reject. And then there's our conclusion summary, kind of going through, okay, what it means to not reject that null hypothesis. I'll probably put paper sleep. Okay. All right. And so then briefly going through looking at that StatCrunch here. I can put up some other examples for you to review as well without me talking, kind of working through. But looking at that information, had we dealt with a problem involving the mean? Close that down for now. We can go stat. T-stats when you only have sample data, sample standard deviation in particular, one sample with summary. And again, you can put your sample mean, that X bar, right? Your standard deviation, their S. Okay, your sample standard deviation S. Your sample size, that N. And then now we're doing a hypothesis test for the mean, mu. So notice the symbol we're using here. As the mean, whether, right, we're seeing that the average, the mean amount is this quantity, the average rent, the average amount of trash that we're producing, whatever it is. The alternative maybe is different than that quantity. We don't think it's equal to that quantity. It's gotten smaller, it's less than, it's greater than, right? And again, whatever value that is, that amount of rent we're paying per month, okay? Your mortgage payment, your insurance costs, whatever it is, okay? So instead of doing confidence interval, now we're doing hypothesis test. Again, I'd have it, I'll show the critical value, significance level right there is your alpha, what we're going to use, and you can compute, okay? So inputting that information, you can do so. Then, if we happen to jump into the next set of problems, if we have two populations that we're comparing, okay, we can look in the text, look online to see how we write, how we notate the hypotheses there. We're going through a very similar set of operations, but now whether it be proportions, the mean, or even standard deviation or variance, if we have two populations, two samples that we're comparing, right, we go to two samples instead, right, same thing with proportion, two sample, and we'll go for two samples with summary. I'll do like the mean work setup here. And now again, from our two samples, you'll see sample one, this first group, it's sample mean, sample standard deviation, sample size. Then for the second group you're comparing, right? Sample mean for group two, standard deviation group 2, sample size. It could be the same, or we have different samples where we have 50 of one group. Maybe we're able to get like 65 of the next group to compare calculation. We don't make sure to keep that open. We don't pool our variances. That's a special case when we start to assume that the standard deviation for our populations are the same, but we never really know that. So I don't pool. But now notice with our hypothesis test, we're looking at that difference. We start off with that difference is 0, that there's no difference, that both those means are the same for our two populations. And then from there, we can start to identify maybe that they're not equal to each other, not equal to, or if we think that the mean for population 1 is bigger, that difference thing about is attracting a big number minus a smaller number, then that difference is going to be greater than 0, right? Mu1 is going to be greater than mu2. Or if we think mu1 is smaller than mu2, population 1 mean is smaller than population 2's mean, then we have that less than 0. Okay? You can also do a confidence interval calculation similar to what we did before for one population, and then similar business there. Okay? So I'm going to leave that with the discussion because those actions are very similar on how we deal with two populations. Okay? All right. So with that said, there's our work for using StatCrunch, dealing with these 5 steps for our hypothesis test. Let me go back to our camera here. All right, so here we go. Looking at those values, finishing up that process with hypothesis testing. Hopefully that was clear. Sorry for that little bobble at the end. But if you have any questions, always reach out, let me know. All right, take care, y'all.